In section 12.3, we'd like to understand how to use polar coordinates when we're computing double integrals. Polar coordinates, we use r and theta, are an alternative to the standard rectangular coordinates x and y. And of course, I imagine you've all seen this before. X equals r cosine theta and y equals r sine theta. Alternatively, x squared plus y squared is equal to r squared, and y over x is equal to tangent of theta. So why do we use polar coordinates? Well, some regions are best suited to using this coordinate system to describe them. And usually that's the case when our regions can be easily described by sort of rays from the origin. So, we have the origin right here, and I have this ray coming out of the origin, and you can see that the region itself has some radial symmetry in this case. Same thing for the unit disk here. In this case, we have this circle off, centered at 1, 0, but again, so we have this notion as if I look at rays coming out of the origin, they sort of behave well with respect to this region. We'll get into more about this later. So the basic polar regions are what you might call polar rectangles. So a polar rectangle is a region in the xy plane that can be described by constant curves in terms of polar coordinates. So when we look at this, this boundary right here is given by theta equals alpha, and this boundary right here is given by theta equals beta. So just constant functions of theta. On the other hand, this curve right here is given by r equals a, which is a circle, and this boundary curve right here is given by r equals b, a circle of a larger radius. So the region right here doesn't look like a rectangle, but if we were to write out polar coordinates in terms of, in the same way that we draw our standard rectangular coordinates, then it certainly would be a rectangle. R ranges from a to b, and theta ranges from alpha to beta, and if we substitute r and theta with x and y, then this would be a rectangle in the xy plane. And so there's a transformation that maps r and theta over to x and y, and it's the standard x equals r cosine theta and y equals r sine theta. It's a standard coordinate transformation from polar coordinates, and so that's why we call this a polar rectangle. So I want to calculate the area of one of these standard polar rectangles, and the way I'm going to do this is I'm first going to label a couple variables in here. So we'll call delta theta the change in theta as a standard, and so it's beta minus alpha, and delta r will be the change in r, which is equal to b minus a. So now I'm going to calculate the area of this polar rectangle, which I'm going to call delta a, because I'm calling these delta r and delta theta, and it's the way we'll treat it when we're talking about integration in a second. So to get at this, I want to sort of make one more remark, which is that if I look at the center of the polar rectangle, and I call the coordinates of this point, the polar coordinates of the point, r star and theta star, then r star is halfway between a and b, so it's the average of a and b. So 1/2 a plus b. And it turns out that this r star is going to show up in our formula for delta a. That's why I'm getting it on the screen. Now, how do we calculate this area? Well, I think about this area as I have this big sector of the circle r equals b over the angle delta theta, and I subtract off the area of this sector of the circle of radius a. Now, if we remember some of our basic geometry, if I make an angle theta and I have a radius r and I have this sector of a circle, the area of this is 1/2 r squared theta. Okay, so that's the formula we're going to use. So now we can calculate delta A. So delta A is equal to the area of the larger sector, which is 1/2 b squared times delta theta, b coming from the radius being b, and delta theta being the angle that we sweep through. And then we're going to subtract off the area of the smaller sector, which has radius a and still has angle delta theta. Okay, so now we just want to factor this. So we have the 1/2, and then we have b squared minus a squared, and then times delta theta. Now b squared minus a squared factors as b plus a times b minus a delta theta. Okay, so now we just have to recognize that all these quantities are things we've already given names. So 1/2 of a plus b, or b plus a, that's exactly what we called r star. B minus a is exactly delta r, so replace this with delta r, and then we have delta theta. So our formula here is that delta a equals r star times delta r times delta theta. So we've come up with this formula for the area of one of these individual polar rectangles. Now we're ready to come up with a formula to compute a double integral over one of these polar rectangles. So we need a function. So suppose f is a function that's from R2 to R that's at least defined on the polar rectangle R itself. So we want to define this double integral of f over r dA, but completely using polar coordinates. So the way we do this is exactly analogous to what we did in our standard rectangular coordinates. So what we do is we partition our region R into these smaller polar rectangles. Each one of these curves is r equals a constant or theta equals a constant. Okay, and so one of these is highlighted here. So the generic one is r sub ij, I, measuring the index for these boxes going this way, and j being the index for these going this way. And then I've sort of marked off this midpoint in here as before. So this is our midpoint, so r star and theta star. Now I'll call this sub ij for each one because it corresponds to the r sub ij. Okay, so we want to compute this double integral over r of f dA. So this is the coordinate-free representation of that, but now we want to get into specifics. So as always, it's going to be a limit as delta r and delta theta go to 0. What are delta r and delta theta? Delta r is the length, this length, and delta theta is this angle. And we're just assuming that delta r and delta theta are constant as we in this partition. You don't have to, but you can certainly get away with it if you'd like. And then we're going to compute this Riemann sum. So we have I equals 1 to m and j equals 1 to n, so this double sum. And then of course what do? We for this sample point, this midpoint, so we're kind of using a midpoint rule here, we're going to evaluate our function at that point. So we have f of r star theta star, and these are both sub ij, and then times delta aij, which is defined to be the area of r sub ij. Alright, so this is the natural thing to do, and now we can just substitute in the formula that we just used for delta a. So we have the limit delta r, delta theta go to 0. We have this double sum. I'm going to be a little bit lazy here. So f of r sub ij star theta sub ij star, and then delta a was r sub ij star times delta r times delta theta. Okay, so we get this extra r showing up in this limit, and that's really the key thing, and that's the key difference. Whereas in rectangular coordinates, delta a would have been delta x, delta y. Instead, in polar coordinates, delta a has this extra factor right here. So this is probably the main thing to notice right here is this term. And so if this limit converges, then we can sort of recognize this, even though it's written in terms of r and theta, this is exactly the formula for the double integral, the iterated integral dr d theta. And so our bounds are from a to b, which of course came from r itself, and our theta bounds are from alpha to beta. And the key is here that we have not only f, but we have this extra factor of r in there. And that really is the main difference from a practical standpoint when you're using polar coordinates, is that you write your function in terms of polar coordinates, and you have this dr d theta, and you come up with your bounds, and we'll talk more about that. But then in the end, I have this extra factor of r that I have to throw into the integrand, just from the nature of how polar coordinates relate to the standard x and y coordinates.